Welcome back to linear algebra. So we've talked about linear systems, we've talked about matrix addition, we've talked about scalar multiplication, things like transpose, diagonal matrices. Now we're going to talk about dot product and matrix multiplication. So matrix multiplication is not like numerical multiplication. Yes, it does involve just standard multiplying of numbers, but it's handled differently. And one of the things that you're going to notice about this is that matrix multiplication does not commute. In other words, I know that 5 times 6 equals 6 times 5. I can do the multiplication in any order, and it ends up being 30. However, if I take a matrix A multiplied by a matrix B, that's actually not the same as the matrix B multiplied by A. It might be, but there's no guarantee that it will be. And in fact, most of the time, it won't be. So that's the one thing that's actually different about matrices than numbers. So let's just jump in, get started, and see what we can do. Okay. So let's go ahead and start with a definition, and this is going to be our definition of dot product, which is going to be very, very important, and it shows up in all areas of science. So we will let equal A1, A2, A3. Let me erase this A3 and just use dot, dot, dot all the way to AN. And B equal to B1, B2, dot, 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 Bn. Okay, so let me just explain what these notation means here. So whenever we see a normally a lowercase letter A, B, C, D, X, we'll often use X with an arrow on top. That means it's a vector. And a vector is just a list of numbers. So A1, A2, all the way to AN. In this particular case, we're talking about an n vector, which means it has n entries. So a 5 vector would have 5 entries. So an example might be, let's say the vector V might be 1, 3, 7, 6. That's all this means. This is the vector, and these are the components of that vector. It's composed of 1, 3, 7, 6. It's a 4 vector because it has 4 entries in it. That's all this notation means. This is just a generalized version of it. Okay, so let A, the vector A, equal A1 through AN. Let the vector B equal B1 through Bn. Now we define something called the dot product as the following. A dot B, the product of two vectors, is equal to A1 times B1 plus A2 times B2 plus dot, dot, dot plus A sub n, B sub n. And I'm going to write this in sigma notation. Sigma notation, I'll explain in just a minute. If you guys haven't seen it, I'm sure you have, but you guys, I know that you don't deal with it all too often. Okay, so if the vector A is composed of A1 through AN, B is the list B1 through Bn, the dot product A dot B is equal to the product of the corresponding entries added together. So when I add these together, I end up with a number. So the dot product of two vectors gives me a scalar. It gives me a number. So I just add them all up. This sigma notation is the capital Greek letter S, and it stands for sum. And it says take the sum of the ith entry of A, the ith entry of B, multiply them together, and add them. So run A1, B1 when I equals 1, and then go to the next one, I equals 2 plus A2, B2, and then go to I equals 3 plus A3, B3. So this is just a shorthand notation for this. We won't deal with sigma notation all that much. In our definitions, whatever we do, I'll usually write this explicitly. I just want you to be aware that in your book you'll probably see this. You'll definitely see it in the future. That's all this means. It's a shorthand notation for a very long sum. So don't let the symbolism intimidate you, scare you, confuse you, anything like that. It's very, very simple. Okay, let's just do an example of a dot product and everything should make sense. So, example, we will let the vector A equal 1, 2, minus 3, and 4. So this is a 4 vector. And we'll let B equal minus 2, 3, 2, 1. Notice I wrote one of them in row form, one of them in column form. This is also a 4 vector because we have 4 entries. I wrote it this way because in a minute when we talk about matrix multiplication, it's going to make sense. Well, it'll make sense why it is that I wrote it this way, but just for now, understand that there's no real difference between these two. I could have written this as a column, I could have written this as a row. It's just a question of corresponding entries. But I did it like this because in a minute, when we do matrix multiplication, symbolically it's going to help make sense when you move your fingers across a row and down a column to sort of keep things straight. Because matrix multiplication, there's a lot of arithmetic involved. Okay, so our dot product, A dot B here, A dot B, we'll just go back to our definition. It says take corresponding entries and just multiply them together. That's all you got to do. So I take A1 times B1, so which is 1 times a negative 2, which is negative 2, plus 2 times 3, which is 6, plus negative 3 times 2, which is minus 6, plus 4 times 1, which is 4. Well, that equals, so the 6's cancel, negative 2 plus 4 gives me a 2. So I have a vector, a 4 vector, times a 4 vector, and I end up with a number, 2. The dot product of two vectors is a scalar, and all I'm doing is multiplying corresponding entries and adding them all up. That's it. Simple arithmetic. Nice and easy. No worries. Let's go ahead and move forward now onto matrix multiplication. Okay, so let me go ahead and write down the definition of matrix multiplication, and then we'll do some examples. We will let A equal that matrix A sub ij, B m by p. So this is an m by p, maybe 3 by 2. Let B be the ijth B, B p by n. So A is m by p, B is p by n. Notice that the number of columns of the matrix A is equal to the number of rows of matrix B. That's going to be very, very important. Then AB is the m by n matrix. C equals C sub ij, such that the ijth entry of C is equal to row sub I of A, in other words, the ith row of A, dotted with the jth column of B. So let's take a look at the definition again. A is a matrix A sub ij, it is m by p. B is a matrix B sub ij is p by n. When I multiply those two matrices, essentially what happens is that the column of the first matrix, the one on the left, cancels the row of the matrix on the right, and what you end up with is a matrix which is m by n. And that matrix is such that the ijth entry is equal to the ith row of A dotted with the jth column of B. That's why this P and this P have to be the same. So, in order to multiply two matrices, let's write this one out specifically. Okay. In order to multiply two matrices, the number of columns of the first must equal the number of rows of the second. And that's what this says. M by P, P by N. The number of columns of the first has to equal the number of rows. That's the only way that matrix multiplication is defined. And what we mean when we say is defined means if they're not the same, you can't do the multiplication. That's what defined means. It's the only way that you can do it is if that's the case. Okay, let's see what we've got. So, for example, if I have a 2 by 3 matrix and I want to multiply it by a 3 by 2 matrix, yes, I can do that because the number of columns of the first one is equal to the number of columns of the second one, and essentially they go away. What I'm left with is a final matrix which is 2 by 2. It's kind of interesting. Now notice, if I reverse them and if I did a 3 by 2 matrix, and if I multiplied that by a 3 by 2 matrix, I'm sorry, a 2 by 3, now it is defined. The number of columns of the first equals the number of rows of the second. So now I end up with a 3 by 3 matrix. Okay? So these are all defined. That'll work. Let's see, 2 by 3, 3 by 2, 3 by 2, 2 by 3. So notice what's happened here. Take a quick look. I have a 2 by 3 times a 3 by 2 gives me a 2 by 2. If I switch these, a 3 by 2 by a 2 by 3, all I've done is switch them. I get a 3 by 3. A 3 by 3 and a 2 by 2 are not the same. So, in general, not only do the dimensions not match, it won't work. AB is not equal to BA. That's the take-home lesson for this. Matrix multiplication does not commute. AB does not equal BA. And we'll actually do an example later on where we can actually do AB and BA, but they end up being completely different matrices. Okay, so let's do some examples. Let's let A equal to 1, 2, minus 1, 3, 1, 4. When doing matrix multiplication, go very, very slowly and go systematically. A lot of arithmetic, lots of room for mistake. Minus 2, 5, 4, negative 3, 2, 1. Okay, so we said that the ijth entry is equal to the ith row of A times the jth column of B. Well, we're looking at here actually let me use black. This is a 2 by 3 matrix, and this is a 3 by 2. So yes, it is defined because this 3 and this 3 are the same, so we should end up with a 2 by 2 matrix. Okay, let's go ahead and put a little thing here for our 2 by 2 matrix. Now, for the first row, first column, this entry, it's going to equal the first row of A dotted with the first column of B. So it's going to be that row and that column. So I take 1 times minus 2. So let me actually write over here. Let's call this so now we're doing the A11 entry, this one right up here. A11 entry equals 1 times a minus 2, which is minus 2, 2 times 4, which is 8, minus 1 times 2, minus 2. So minus 2 plus 8, answer should be 4. So 4 goes there. Now let's do this entry, which is the first row, second column. Well, the first row, second column means I take the dot product of the first row of A and the second column. So A12 entry is equal to 1 times 5, which is 5, 2 times negative 3, which is negative 6, minus 1 times 1, which is minus 1. Let's try this again without these little extra lines. 1 times 5 is 5, 2 times minus 3 is minus 6. Minus 1 times 1, minus 1. So 5 minus 6 is minus 1, is minus 2. So this becomes minus 2. Now we're going to go to the second row, first column, which means we do second row, first column. This is A, 2, 1. 3 times minus 2 is minus 6. 1 times 4 is 4. 4 times 2 is 8. So 8 plus 4 is 12. 12 minus 6 is 6. So this entry is 6. And now we have our last entry, which is the 2, 2. So the 2, 2 entry, second row, second column, which means we dot product the second row with the second column. Second row of A, second column of B. 3 times 5 is 15. 1 times minus 3 is minus 3. 4 times, oops, that's nice. 4 times, you know, is that a minus 1? I don't even know. No, it's 1. 4 times 1 is 4. So we get 15 plus 4, which is 19. 19 minus 3 is 16. So this entry is 16. So the product, so AB is equal to 4 minus 2, 6, 16. 2 by 3 matrix multiplied by a 3 by 2 matrix gives us a 2 by 2 matrix, and we get that by this row, this column, this row, this column, and then this row, this column, this row, this column. That's all you're doing, rows and columns. Now you know why I arranged it. Remember a little bit back when we did dot product, I arranged it the first one horizontally and the other one vertically. This is the reason why. Because when we multiply, we're doing this times that, this times that, this times that. We can move one this way, one this way. It seems sort of, it's a way of keep things separate. As one hand, one finger moves across a row, the other finger should move down a column, as opposed to going this way or this way. Okay. Let's do another example here. We will, okay, let A equal, this is going to be a 3 by 3, so it's 1 minus 2, 3, 4, 2, 1, 0, 1 minus 2. And B is equal to, let's make it a 3 by 2. So this is a 3 by 3. And then we have 1, 4, 3, minus 1, minus 2, and 2. So this is a 3 by 2. So AB, A times B, is defined. So AB is defined, and it's going to be, well, 3 goes away, the 2 inside ones, so we're left with a 3 by 2. So AB is a 3 by 2 matrix. Okay, well, let's just multiply it out. This time we're not going to write everything out, we're just going to do the multiplication and keep it straight to our final numbers. So we know that we're looking for a 3 by 2, so let's just start putting in entries. Well, the first entry, first row, first column, is going to be first row, first column. So 1 times 1 is 1, minus 2 times, so 1 times, that's 1, minus 6 is going to be, that's a minus 5, and then minus 6 is going to be minus 11, so it's going to be minus 11 there. And now we're going to do the second entry, okay? The first row, second column, which means first row of A, second column. 1 times 4 is 4. Minus 2 times minus 1 is 2. 4 plus 2 is 6. And then 3 times 2 is 6. That becomes 12. When we continue on this way, we end up with 8, we end up with 16, we end up with 7, we end up with minus 5. That's our AB. Okay, now let's try something. let's let A equal to 1, 2, minus 1, 3. And we'll let B equal to 2, 1, 0, 1. In this case, because this is 2 by 2, and because this is 2 by 2, both AB and BA, they're both defined, so I can do the multiplication. Well, let's do the multiplication and see if AB equals BA. So there are two ways that you can sort of demonstrate non-commutativity, is if the dimensions don't match when you switch them, or if it's defined, multiplication is defined and doable this way and that way, then you might end up with different matrices. Again, proving that it doesn't commute. All right, let's see what we've got. When we do AB, okay, we end up with the following. We end up with 2, 3, minus 2, 2. And when we do BA, which as we said is defined, we end up with 1, 7, minus 1, 3. AB and BA are not the same. AB does not equal BA. Matrix multiplication does not commute. Okay. So now let's talk about matrices and linear systems. So we introduced linear systems in our first lesson. We talked about matrices in our second, and we've just introduced matrix multiplication. So now let's combine them together to see if we can take a matrix and represent it as a linear system, or a linear system and represent it in matrix form. So let me go back to blue here. We will let, excuse me, A equal A11, A12, A13, A21, A22, A23, A31, A32, A33, and we will let x with that little line, the vector, be our vector, let's call it x1, x2, x3. This is the vector formulation, this is the component form. It's just a 3 vector. Okay, so this is do this in red, this is a 3 by 3 matrix, and this is a 3 by 1, right? So if I multiply this matrix by that vector, AX, well, it's just a 3 by 3 times a 3 by 1. Well, those are the same, so I end up with a 3 by 1. It is defined, and it's going to equal some vector B, which is going to be a 3 by 1 vector, just something with 3 entries in it, a 3 vector. And let's let B, therefore, equal, we'll call it B1, B2, B3. So again, we have a matrix. We have this 3 vector. I can multiply them because matrix multiplication is defined. Their answer is going to be a 3 vector. So we'll call that 3 vector B, and we'll call its components B1, B2, B3. Okay, well, let's actually do the multiplication here. So AX, when I do this multiplication, this row, this column, this row, this column, this row, this column, here's what I get. A11 times x1 plus A12 times x2 plus A13 times x3. That's what I get. That's the multiplication. A11 x1 plus A12 x2 plus A13 x3. And then I do the second row, that column again. I get A21 x1 plus A22 x2 plus A23 x3. And then I'll do the third row, which is A33 x1 plus A32 x2 plus A33 x3. That's going to be my matrix. That's my actual matrix multiplication. Well, I know that it equals this B. So I write B1, B2, and B3. Well, this thing equals this thing, this thing equals this thing, this thing equals this thing. That's what this says. This is just a 3 by 1 in its most expanded form. That's the A times the X. This thing is the B that it equals. And so now I'm just going to set corresponding entries equal to each other. This whole thing is equal to that. So I write a11 x1 plus a12 x2 plus a13 x3 is equal to b1. And a21 x1 plus a22 x2 plus a23 x3 is equal to b2. And I'm sorry about all the little extra little lines here that are showing up. Try to write a little bit slower. a31 x1 plus a32 x2 plus a33 x3 equals b3. Well, take a look at this. This is just a linear system. That's it. It's just a linear system. You've seen this before. This is 3 equations in 3 variables. x1, x2, x3, x1, x2, x3, x1, x2, x3. These a11s, a2, all of these are coefficients, and these are the actual solutions. So, so you can actually write a linear system as a matrix. So it looks like a11, a12, a13. This is the coefficient, the matrix of coefficients for the linear system. a21, a22, a23, a31, a32, a33. And then you multiply it by the variables, which are x1, x2, x3, and it equals b1, b2, b3. So we can take a linear system and represent it in matrix form. We take the matrix of coefficients, so this is the coefficient matrix, m by n, in this case it's just 3 by 3, but it can be anything. This is the matrix of variables. This is the variable matrix. And it's always going to be some n vector, some n vector. And this is just the, you might call the solution matrix. It's not really the solution matrix. The solution matrix is once you find x1, x2, x3, those are going to be your solutions. So you know what? Let's not even give this a name. Let's just say this happens to be the, well, whatever it is. It's the B that makes up the linear system on the right side of the equality. Okay. Now, given this, we can actually form, as it turns out, we can form a special matrix. If we attach B1, B2, B3 to the coefficient matrix. Okay, now we're going to write this out one more time. So I'm going to take this thing and I'm going to add it as another column to this matrix. So I end up with A11, A12, A13, B1, A21, A22, A23, B2, A31, A32, A33, B3. And sometimes we put like a little dotted line there just to let you know that this is, and this is called an augmented matrix. All I've done is I've augmented my coefficient matrix with my solutions on the right for the linear system. That's all this is. And we do separate it. Sometimes you can see a solid. I tend to put a solid line. That's just my personal preference. Some people don't put anything at all. Again, it's completely up to you. So therefore, any linear system can be represented in matrix form, and vice versa. Any matrix with more than one column can be thought of as forming a linear system. So let's see what we have here. An example. minus 2x. As a system, minus 2x plus 0y plus z equals 5. And then we have 2x plus 3y minus 4z equals 7. We have 3x plus 2y plus 2z equals 3. So this is our linear system. And now let's break it up in matrix form. We have, so we want to write it this way, A, x equals b. This is the matrix representation. A matrix A times a vector b gives us a vector b. So A, the matrix A, is going to be the coefficients. It's going to be, the 2, the 0, the 1, the 2, the 3, the negative 4, the 3, the 2, the 2. Negative 2, 0, 1, 2, 3, negative 4, 3, 2, 2. That's our coefficient matrix. X, let me do this in red. Oops. X is going to be our variables. Our variables happen to be x, y, and z. So that's going to be x, y, and z. And b, let me go back to red. Our b vector is going to be 5, 7, 3. 5, 7, 3. And that's it. You can represent, now we'll do the augmented matrix, which means take the coefficient matrix and add this to it. So we end up with A augmented with B. It's symbolized like that. It is equal to minus 2, 0, 1, 5. And I'll go ahead and do a solid line because I like solid lines. 2, 3, minus 4, 3, 2, 2. You have your coefficient matrix, and you have your matrix that represents the linear system that was originally given to you like that. Now let's see. Now let's go the other way. Let's say we have a matrix 2, minus 1, 3, 4, 3, 0, 2, 5. Let's say you're given this particular matrix. This particular matrix actually can represent a linear system. So we can take a linear system represented in matrix form, which we just did. We can take a matrix and represent it as a linear system if we need to. This ends up being, so let's say that this is the augmented matrix. So that means this is 1, 2, 3. That means we have 3 variables. That's what the columns represent, are the variables. And these are the equations. So we have 2x minus 1y plus 3z is equal to 4. And then 3x plus 0y plus 2z equals 5. Linear system, matrix form. Matrix represents a linear system. Excuse me. Here you go. Okay. So let's talk about what we did today. Recap our lesson. We talked about the dot product of 2 vectors, and a vector is just an n by 1 matrix, either as a column or a row. It doesn't really matter. What you do is you multiply the corresponding entries in the 2 vectors and you add up the total. The dot product gives you a single number, a scalar. It's also called the scalar product. So dot product, scalar product. As you go on in mathematics, you'll actually refer to it as a scalar product, not necessarily a dot product. After that, we talked about matrix multiplication, where we actually invoked the dot product. So with matrix multiplication, you can only multiply 2 matrices if the number of columns in the first matches the number of rows in the second. Matrix multiplication does not commute. In other words, A times B does not equal B times A in general. It might happen accidentally, but it's not true in general. The ijth entry in the product is the dot product of the ith row of the first and the jth column of the next. Okay. Now, matrix representations of linear systems. Any linear system of equations can be represented as an augmented matrix. You take the matrix of coefficients and you add the column of solutions. Any matrix with more than one column can represent a linear system of equations. That last column is going to be your solutions. That's the augment. Okay. So let's do one more example here. So we will let A equal to 3, 5, 2, 4, 9, 2, excuse me, and B equals 1, 0, 1, 6, oh, she knows, 2, 1, 3, 7. So here we have a 3 by 2 matrix, and here we have a 2 by 4 matrix. So yes, the 2's on the inside are the same. They end up canceling, and it's going to end up giving us a 3 by 4 matrix. So we're left with the 2 outside. So we're going to be looking for a matrix which is 3 by 4. It's kind of interesting if you think about it. 3 by 2, 2 by 4, now you get a 3 by 4. You get something that's like bigger than both in some sense. Okay. So AB is equal to, well, we take the first row, the first column. 3 times 1 plus 5 times 2. 3 times 1 is 3. 5 times 2 is 10. You end up with 13. First row, second column. Well, you take the first row, dot product with the second column. 3 times 0 is 0. 5 times 1 is 5. So you end up with 5. And then you keep going. You end up 18, 53, 8, 4, 14, 40, 13, 2, 15, and 68. So our product AB is equal to this matrix. Notice, A times B is defined. If I did B times A, well, B times A is equal to a 2 by 4 times a 3 by 2. This 4 and this 3 aren't equal. BA is not, it's not even defined. We can't even do the multiplication, leave alone find out whether it equals or not, which in general it doesn't. So in this case, it's not even defined. It only works when A and B are such that A is on the left of B, B is on the right of A. And they'll often say that. We'll often say in linear algebra, multiply by this on the left, multiply by this on the right. We don't do that with numbers. We just say multiply the numbers. Okay. Now, let's let the variable, let's let x, the vector, equal to x, y, and z. And let's let the vector c equal to 4, 2, and 9. Now, we want to express, well, actually, you know what? Let's go. We want to express Ax equals c as a linear system and as an augmented matrix, both. So we have a matrix A, that's this one. We have a matrix X, we have a matrix C. We want to express Ax equals c as a linear system and augmented matrix. Okay. Well, wait a minute, that's not even going to work. So we can't even do, this has 3 and 2, so this can't be x, y, z. This is going to have to be x, y. My apologies. X, y. There we go, because this is 3 by 2, this is 2 by 1. Yes, we want the multiplication to be defined. So we end up with 3, 5, 2, 4, 9, 2 times xy equals 4, 2, 9. So you end up with, well, 3x plus 5y equals 4. 3x plus 5y equals 4, because you're doing the first row, first entry, first row, first column. 2x plus 4y, 2x plus 4y equals 2, and 9x plus 2y, 9x plus 2y is equal to 9. All we've done is go this times that equals that, this times that equals that, this times that equals that, and we end up with our linear system. Now we want to convert that to an augmented matrix. Well, we take 3, 2, 9, 3, 2, 9, 5, 4, 2. That's our coefficient matrix, right? And we augment it with our solution matrix, 4, 2, 9. 4, 2, 9. That's all we've done. A, B. A times B, it is defined. We can find the multiplication. We can take given x and given c, this is a 2 vector, this is a 3 vector. We can take AXC represented as a linear system. We express it this way, we do the matrix multiplication, we set corresponding things equal to each other, and we've actually converted this to a linear system. So this and this are equivalent. And we can take this linear system and express it completely just as a matrix, an augmented matrix, by adding the solutions as the augment on the right, and we end up with that. Okay. Thank you for joining us today for linear algebra and our discussion of dot products and matrix multiplication and linear systems. Thank you for joining us at educator.com. We'll see you next time. Bye-bye.